Thank you and good afternoon. A little bit about myself. I've been in underground construction for 27 years. My primary focus has been on materials design, trenchless methods for applying cementitious materials, epoxy resins, also cured in place pipe type apparatus. This was an interesting project in that it was obviously a buried bridge, but it's not too often that we see parallel pipe stacked next together, at least not for where I'm from in the middle of Iowa. But Castle Rock is the location of this project. It's Plum Creek Drive Parkway. It's a very heavily traversed artery throughout the town of Castle Rock. And if anyone's familiar with the area, it has really taken off in population growth over the years. In 2020, the population was approximately 70,000 people, which was an increase of approximately 51% over 2010. So it's a very rapidly growing community. These 6 structures varied in size. They're actually 5 or 96 inch in diameter, and then there was a 145 inch arched pipe. Average length of all 6 were approximately 172 feet. Again, it's a situation where it's the local government that owns the structure. Colorado DOT does the inspections. In this situation, they had just gone through an inspection, and a few deficiencies were found in the structure. Mainly the issues were the inverts were gone through abrasion, corrosion. The majority of the invert was gone, wrapping its way up through the spring line areas of most of the pipe. The town was able to actually secure some federal funding, so that's what ended up paying for the project. And the collaboration was with the Colorado DOT, Town of Castle Rock, engineer of record was Wilson and Company, and American West Construction was the actual contractor that did the installation and site work. A couple of things I wanted to work on this particular project was, how can we renew this without actually being too disruptive to the community since it's carrying so much traffic. So service disruption was a concern, but there was also some structural deficiencies in a couple of these culvert pipe. So they wanted to make sure they had a structural fix where needed, very small staging area, not a lot of room to operate with this installation site. Also needed to maintain flow requirements. They couldn't, capacity was fine, but they couldn't reduce the diameters to where they could have some flow problems. Again, pipe configuration, 596s, a 145, so the flows through that area were a little bit interesting, just from a bypass proposition. But obviously then the biggest concern was cost. How much is this going to cost us to repair? And based on what do we have for money? It always comes down to money at the end of the day. But based on what they had for budget, what they were able to get for funding, they were able to fully structurally rehabilitate 3 of the structures. So they focused on the 145 and 2 of the 96s. The other 3 were deemed to be in fairly decent shape, but would benefit from an invert paving. So that's how those 3 structures were approached. So methods that they evaluated, dig and replace, cut and cover. So they looked at actually removing the structure. Obviously, it would meet the structural requirements, but the disruption to traffic was just not a place they could go. Actually was looking at coming in a little bit more costly than they had anticipated as well. Next one they looked at was a cured in place pipe, basically a fabric soaked in resin, inflated with a bladder, and then using steam or hot water, the tube is cured into place, creating a plastic pipe inside the structure. Met the structural requirement, but as you can see from the photo, it takes up a lot of space. Literally in this instance, they're closing the roadway so they can position the wet out liner and get it pulled through the pipe. It's not easy. It really is a dance when you see what these guys do with either backhoes or cranes. It's quite an impressive process to see installed. But again, too disruptive, too costly. Also looked at slip lining with a high density polyethylene pipe. met the structural requirements, but the diameter they were going to lose was going to be prohibitive. They weren't going to be able to lose that kind of flow capacity. Now, a lot of times with an HDPE insert, you actually gain a little bit because the smooth surface allows for a lower Manning's coefficient. But in this instance, it wasn't going to be enough to accommodate what they needed for flow capacity. With the environmental considerations they had, a site of the area, most of the time this is a large, periodically dry stream. During the rehabilitation portion of the project, it did have some small flows in it. It is in a 100-year floodplain. It's also empties into a wetland area, so they had to be very, construction methods had to be very conservative to make sure we didn't damage the area. Any of the approaches to the stream, basically it's very steep erosive banks and a capacity to flood quickly. So even from a construction phase, we were always watching the weather to make sure we didn't have a flood event sneak up on us. This is a photo of the outlet from the head wall. Obviously, you can see the wetland area. In this instance, it was actually fairly wet and had a pretty good flow through it. On the whole setup of the construction site, flow control was a major component. Also protecting the wetland, and then creating a staging area that wasn't going to be unable to be put back into a native grass and native soil situation. So at the end of the day, those red boxes indicate what we had for staging area, not a lot of room. We basically bypassed through one pipe while we worked on the others, and then once we got the others completed, we would move the bypass over and finish the last one. We would work from downstream and pull the apparatus from downstream upstream. So most of the mixers, materials were actually up in that upper left-hand corner. Everything else at the bottom was basically containment type setups, berms, and making sure that we didn't lose anything into the streams. At the end of the day, the certificate cast concrete pipe method was chosen to be the rehabilitation method. It's also known as spray applied lining materials. The product that was used was a Centrapipe PL8000 material and a PL8000 12,000 material. Both materials are used at different aspects of the rehabilitation process, which I'll talk about here in a little bit. Total thickness on this design calculated out to 2 inches, so 4 inches of diameter were lost on these structures that received the full lining. So very minimal reduction in size. We did take the corrugations out of play when we do this process, so that actually smooths the pipe out and actually increased the flow capacity of these particular pipe. Also during this thing, small staging area, bypass pumping, construction done off the roadway. Never had to divert traffic or close the road, so everything maintained open while we were doing the project. So the material that we used for the main lining was PL8000. It's a fine aggregate composite concrete, very high strength material. We see strengths a minimum of 8,000 PSI. It's very low permeability. Coulomb ratings on this material have tested as low as 50. Very good freeze thaw resistance, 300 cycles, no damage. It's very thixotropic, so we're able to mix and pump this material, maintains a very good fluid ability, and we're able to pump it through rubber pipe and hose, roughly 400 feet. If we start adding steel pipe to the mix, we can pump this material out to 600, 800 feet. But because it's fluid while it's energized, it also it has an interesting effect when it impacts these pipe as we rehabilitate them. It tends to flow into the lowest point, so it fills in the valleys of the corrugations first, then builds out, and then begins to increase that thickness above the peak corrugation. But it conforms to whatever geometry we apply it to. So we'll even find that if we're applying it into a square structure, it actually conforms to the shape of the square, and although the corners are somewhat rounded, it still maintains its square geometry as we apply the material. But once it comes to rest, it gels. So it becomes almost like a modeling clay just a few seconds after it's applied. So that allows it to stay in place, maintain its adhesion, and then cure into the concrete shell. Works out great in these types of situations for application, fairly quick and easy to get it placed. I think we're able to pull about 200 feet a day, sometimes a couple of passes. In this instance, we just move from one pipe to the other so we can continue the process. Again, a lot of the work wasn't even lining the pipe, it was creating staging area. So we had to create some pads to stage the equipment, definitely level pads for the pump and mixer to make sure we had a good stable platform for that process to occur. And then we just needed areas to park vehicles and other equipment off the roadway so we weren't interfering with the traffic. Again, bypass was set up to flow through one pipe while we worked on the others. And then once the others were completed, the bypass was shifted so that we could work on the last pipe. Basically, bypass was set up by creating a berm on each end so we could divert the flow into one and then just easily remove it with a small excavator to reinstate. Once the bypass was set up, it was then a lengthy process of just removing the silt. Several feet of silt had accumulated in all 6 of the sections over the years that had been in service. We used jetters, vac trucks. Also, in the last slide, you could see a small stand-behind skid steer that was used to muck out the material in the pipe. First thing we do once we start repairing these pipes is we look at what do we have for voids. In this instance, we were fairly fortunate that the voids weren't too extreme. We were able to fill most of them with rapid setting patching materials. If we had any kind of a small leak, we were able to stop them with a rapid setting plug material. If we'd gotten into some real heavy active leaks, we would have used a chemical injection grout. But in this instance, the pipe had been dry enough, long enough that we weren't really continuing with too much groundwater with this repair. We did fill any holes. We did not notice or find any voids behind the pipe as far as any soil envelope issues. If we do find those soil envelope issues, we will do a grouting with the polyurethane soil stabilization grout to make sure we reinstate that soil envelope around the pipe. Once we got to that portion, we always start with repairing the invert. In this instance, we're using a PL 12,000 material, self-leveling, finds its way into the lowest point. Depending on the shape of the invert, sometimes we remove rotten steel. In this instance, we just had intermittent areas of rotten steel, so we removed a little bit. Otherwise, we just pumped the PL 12,000 into the invert, let it find its level. It flowed underneath the invert and then built its way up through the voids. And then we created a 2 to 3 inch new paved curb inside of the structure. This process was then carried out and left as is for 3 of the 96-inch diameter structures. Really just looked at needing a new surface for the invert. From there, we actually start pulling the apparatus through. So it's a bidirectional spin caster, spins clockwise and counterclockwise. We do make multiple passes. We aim to achieve a 1/2 inch thick liner for each pass. In this instance, we were working to get a 2-inch liner, so we made approximately 4 passes to get to the achieved liner. In this picture, it's a little blurry, a lot of dust in the air, but you can kind of still see some of the ribs of the corrugation in the pipe. But as we're pulling through with this, this secondary pass, you can see that starts to smooth out, and you start to see those corrugations disappear to smooth the pipe out. Again, the design thickness was calculated at 2 inches. And we applied approximately 4 layers. And again, it's roughly about 200 feet per day at a 1/2 inch, and then we would move to the next pipe to carry on the process to the adjacent structure. Close-up view of the centrifugal application, the process. You can see the radial spray as it comes off the spin caster. Spin caster rotates this one rotates at about 7,000 to 8,000 RPM, so we get a very nice impact when the material hits the wall. And that allows it to conform to those geometric shapes. As far as quality control goes, we did a couple different things on this project. One, we use thickness gauges. So we have a an adhesive plastic gradiated measuring stick, basically, that gets attached at different locations within the pipe. So we have a visual reference to make sure that we've covered those up. We know we've achieved the correct thickness. We also did mathematical tracking. We have a known pumping rate, we have a known retrieval rate and application rate. So just by the amount of material we were using per linear foot, we were able to know that we were on the right track for applying the material. We also took some random core samples throughout the pipe, so then we're able to get calipers onto the cores and get a good measurement of thickness. Gives you another indication that you've got a tightly fit liner in that pipe, because you can look into the hole that's created and see whether or not you've got a good tight liner in place. Lastly, just to verify that the materials are being mixed correctly, we randomly took samples during the day and did ASTM C109 compression cube tests. Just to verify strengths they come in line. It's just to verify that the appropriate amount of water are being used to wet the product out. Typically what we see is if it's overwatered, we typically see the strengths drop. If it's underwatered, we typically see strengths increase. Typically the increased or underwatered isn't a structural issue, but it can be an installation and performance issue for the contractor. It becomes harder to pump, and the texture isn't as nice at the end of the day. I should back up a little bit on design. In these instances, we looked at the load response for these pipe, and they were all in compression. So that's why compression was the value we were really looking at for our quality control. If we get into a beam and bending situation, then we want to start looking at the flexural strength. So then we'd be looking at C78 beams to do tests on for our quality control in the field to verify we're reaching the strengths that had been allocated for design. And this is the final product. Rusted corrugated metal pipe was then turned into a brand new concrete pipe. Finish is basically as is. The profile that's left behind by the spin caster is roughly an orange peel finish. But as far as an estimate for a Manning's N coefficient, we typically figure an average of about a 0.017 for the coefficient. Very cost effective, came in under budget. Again, no disruption to traffic, maybe a minor delay if we were placing materials and unloading a truck. So a few minutes of disruption was basically all the residents had to contend with. And then we're looking for a long-term, rehabilitation out of this process. And that will conclude the presentation. I'll open it up for questions.
Great presentation, thank you. I was just wondering, how does the inspection process now change that it has the lining?
That's a good question. I don't know. Quite honestly, I don't know. I suspect instead of looking at it, it's probably a composite now, right? So they're probably looking for, concrete pipe. So you're going to inspect it as a concrete pipe. And then if you're seeing cracks and rust, whatever you can still see of the corrugated metal pipe, and you're probably going to be looking at that as well. Realistically, what we designed this for, though, is to assume that corrugated metal pipe's eventually going to dissolve away to nothing. So the liner is designed to take all anticipated loads in that structure as is. It's probably going to be looked at as a concrete pipe now.
So, sorry. It's not you're not, the concrete that you're pushing, it's not pushed at a pressure, and that's what actually, it's the centrifuge.
Correct. The centrifugal force coming off that applicator is what's driving the force.
So you're not pushing the grout at a certain pressure in order to do that?
Well, it's pressurized, but it's an open-ended hose, so it loses pressure as soon as it comes out the end of the hose. So pumping pressures are anywhere from 2,500 to 2,600 psi. So it's quite a bit of pressure to push it down the line, but that's not actually what's the force you're seeing as it hits the wall.
Huh. Okay. That's good.
It's like it's slinging it.
All right, well, thank you all very much.